In this module, we will learn the fundamental principles of electrochemistry that form the basis of batteries. We will examine how chemical energy is converted into electrical energy, the roles of electrodes and electrolytes, and how cell potential is generated. In addition, we will highlight the importance of batteries in everyday life and their diverse applications across different fields. The story of batteries begins in 1800 with Alessandro Volta. His invention, the Voltaic pile, demonstrated for the first time that chemical energy could be transformed into electricity. The pile consisted of alternating zinc and copper discs, separated by cloth soaked in salt water or acid solution. These layers created a continuous flow of electrons, generating a steady current. This simple yet revolutionary device laid the groundwork for modern electrochemistry and all battery technologies we use today. Batteries are at the very heart of modern technology. They power our phones, laptops, and electric cars, while also enabling renewable energy storage. By learning their chemistry, we can design safer, longer-lasting batteries and develop sustainable recycling methods that support the global transition to clean energy. Every battery shares the same basic architecture. First, we have the anode and cathode. These are the main players in the battery's chemistry. The anode is the negative electrode where oxidation occurs, releasing electrons. The cathode is the positive electrode, accepting electrons during the reduction process. Their roles are critical in facilitating the flow of electrical energy. The current collectors are metallic foils that link the electrodes to the external circuit, allowing the flow of charge. They ensure that the energy produced within the battery can be harnessed effectively. Next is the separator, which plays a protective role by preventing direct contact between the anode and cathode, thus avoiding short circuits. Think of it as the peacekeeper within the battery. And finally, the electrolyte. It conducts ions between the electrodes while blocking electron flow internally, maintaining the battery's internal stability. Together, these components form a closed system that enables the safe flow of charge, making our modern devices possible. These elements work harmoniously to power everything from our mobile phones to electric vehicles. Electrochemical cells, the dance of oxidation and reduction. Electrochemical cells operate through a collaboration of oxidation and reduction processes. At the anode, electrons are released. At the cathode, electrons are consumed. Ions travel within the electrolyte, while electrons flow through the external circuit, and this synchronized movement produces the electricity we rely on daily. Different battery chemistries rely on specific combinations of electrode materials and electrolytes. Let's take the lithium-ion battery as an example. During discharge, lithium ions move from the anode, which is typically graphite, to the cathode, usually lithium cobalt oxide. This movement releases electrons, generating power. The ability of a battery to recharge efficiently, and repeatedly, significantly impacts its lifespan and efficiency. Now, looking at the processing of spent batteries, it involves several steps such as mechanical pretreatment and acid leaching. These processes help in the recovery of valuable materials like zinc, manganese, and cadmium. It's important to note that during these processes, careful handling is required to manage hazardous gases and ensure environmental safety. Understanding these reactions and processes helps us appreciate the complexities behind the simple act of charging our devices. Primary batteries are non-rechargeable. They're designed for single use, continuing until the chemical reactants are fully depleted. Common examples include alkaline and zinc-carbon batteries. On the other hand, secondary batteries are rechargeable and can go through numerous charge-discharge cycles. This includes familiar types like lithium-ion, nickel metal hydride, and lead-acid batteries. These offer a significant advantage in terms of cost per use and sustainability, given their ability to be reused hundreds, if not thousands, of times. Think about the devices you use daily. Many of them likely rely on secondary batteries. This capability not only extends the life of the battery but also reduces waste, contributing to a more sustainable environment. Energy density, measured in watt-hours per kilogram, indicates how much energy a battery can store per unit of weight. This is crucial because a higher energy density allows for longer runtimes without increasing the size or weight of the battery. Consider this comparison. Lithium-ion batteries offer an impressive energy density of 150 to 250 watt-hours per kilogram, whereas lead-acid batteries only provide between 25 and 50 watt-hours per kilogram. This stark difference explains why lithium-ion batteries are often favored for portable devices and electric vehicles. However, energy density isn't the only factor in performance. Charge and discharge rates, how well a battery handles different temperatures, and its cycle life, all play significant roles. Balancing these elements is essential for designing effective batteries for various applications. Batteries depend on critical materials like lithium, cobalt, and nickel. Their mining causes pollution, habitat loss, and emissions, and since they are limited, shortages may occur as demand grows. So, what can we do? Recycling and material recovery reduce waste and save resources. Giving batteries a second life in homes, storage, or e-mobility is another solution. In the end, adopting a circular economy, design, use, reuse, recycle, is essential for sustainability and responsible battery end-of-life management. Let's wrap up with a quick summary. Batteries convert chemical energy into electricity through redox reactions. They have four key parts: anode, cathode, electrolyte, and separator, which together create cell potential. We looked at different chemistries: alkaline, lead acid, lithium-ion, and nickel metal hydride, each with unique uses. Primary batteries are single-use, while secondary ones are rechargeable. Energy density is vital, explaining why lithium-ion dominates portable devices and EVs. And finally, sustainability matters. Recycling and the circular economy help conserve critical materials like lithium, cobalt, and nickel. Thank you for your attention. Always keep in mind, every step we take in energy and sustainability today helps shape a cleaner, smarter, and more resilient tomorrow.